So let's just quickly summarise where we've got to so far, and then I'll state some results which kind of complete the treatment of cyclic groups. In fact, although you may not think so at the moment, cyclic groups are actually very straightforward groups in the sense that we know all there is to know about cyclic groups, which is not true for groups in general. So remember, the idea is a group is cyclic, so just remind you of the definition, if and only if it can be generated by a single element. So this is the basic idea. And remember, generated means that it consists solely of the powers of this single element. So to use the notation we've been using for a couple of weeks now, we use this pointed brackets notation, and remember that means, well, to use sloppy notation, that means the set of all powers of A, all in a bag. That's slightly sloppy notation. To be a bit more precise, it's the same as the set of all group elements that can be written as a power of A for some integer n. So n can be negative, 0 or positive. So these are particularly straightforward groups. One element generates the whole thing. And as we've seen from examples, a cyclic group by definition has one generator, but it may have more than one generator. In fact, as soon as it's big enough, it'll have at least two generators. But the point is it's got one generator at least. So that's the definition of a cyclic group. We've seen several examples, and we've actually proved a theorem that tells us what cyclic groups look like. So we know, in this sense, we know what cyclic groups look like. So this is a theorem that we proved last time. We actually almost got to the end of the proof. We didn't quite finish the proof. Well, there are two possibilities. Either G is finite or G is infinite. So if G is infinite, and G is isomorphic to the cyclic group Z. So this is the integers under addition. So that's a very basic example of a cyclic group, and in fact it's essentially the only cyclic group if we're talking about infinite cyclic groups. And remember that the integers has got precisely two generators. Every integer is a multiple of 1, and it's also, every integer is also a multiple of -1, and 1 and -1 are the only generators for the integers. Remember, we're using additive notation here, so rather than saying a power of 1 or a power of -1, I use the term multiple. I've mentioned that issue about notation a few times. So one possibility is that G is an infinite cyclic group, and the only one is the integers. So that's very easy. The only cyclic group that's infinite is the integers, up to isomorphism. And in group theory, if two groups are isomorphic, remember that means there's a bijection between them that preserves the binary operation. If two groups are isomorphic, then as far as group theory is concerned, they're the same. The only difference might be that rather than labelling the elements by integers, we've labelled them in some other way. But as far as group theory is concerned, they're the same. So there's only one infinite cyclic group. Okay? So that's very straightforward. And it's one that we know and possibly love, the integers under addition. Okay? If G is finite, then the only thing we need to know is the order of G, how many elements there are in G, and it's isomorphic to the integers modulo n, where n is the order of G. So if G is a cyclic group of order 17, then essentially it's the same as integers modulo 17 under addition. There's only one possibility. So this is the integers modulo 17. Oops, not 17. I've got 17 on the brain now. Modulo n in general under addition. Addition modulo n. So this is a bit more complicated because although we've been treating, as Fraley does, the elements of Zn as integers, so from 0 up to n minus 1 with addition modulo n, really those elements 0, 1 up to n minus 1 are not integers, they're actually equivalence classes of integers where we regard two integers as equivalent if they differ by a multiple of n. But in any case, we understand integers modulo n, so this is clock arithmetic where your clock has n spaces. So we understand this one as well. So those are the two possibilities. Infinite, it's isomorphic to z. Finite, it's isomorphic to integers modulo n. Okay? So in that sense, cyclic groups are straightforward. The only ones you need to understand are z and z modulo n. And it's actually z modulo n which is more interesting because the number of generators needs to be determined, whereas with z it's always precisely 2 generators. Okay, so that's the structure of cyclic groups, and we did prove that theorem last time. Now, once we know what cyclic groups are, the next thing to ask about is the cyclic groups, their subgroups, the subgroups of cyclic groups. And we've actually proved a result already. And another nice thing about cyclic groups is if you take a subgroup of a cyclic group, then that has to be cyclic as well. Okay, so that's nice. So the first result, which we actually proved last time, and remember we used a bit of number theory to prove this, we used the division algorithm where you divide one integer by another and have a quotient and a remainder. So there was a bit of number theory coming in here. So let G be a cyclic group. And let H be a subgroup of G. Then H is a cyclic group. If you wanted to put the word also in for emphasis, you could do. So subgroups of cyclic groups are cyclic, so that's quite a nice result. And we actually proved that last time. And just to remind you a little bit about the ingredients in the proof, if G is generated by A, then actually H is generated by, well, H is generated by some element of G, of course, because it's a subgroup of G. And in fact, it's generated by A to the S, because every element of G is a power of A. And H is generated by that power, S, where S is the smallest positive power of A that belongs to H. So that was an ingredient in the proof. So this notation looks a bit complicated, but all I'm saying here is I look at powers of A and I look at the first positive power that actually belongs in the subgroup of interest, and that first positive power, S, is such that A to the S actually generates A. So not only can we say that A is cyclic, but we can actually say what H is generated by. It has to be generated by some power of A, because every element of G is a power of A, and the power of A that generates H, well, there might be more than one generator, but certainly a power of A that generates H is this first positive power that belongs to H. Okay, so we actually proved that last time, and this is true whether G is infinite or finite. So in the case of an infinite cyclic group, so a corollary to this theorem, which I also mentioned last time, I think. So if G is an infinite cyclic group, well, since we know that infinite cyclic groups are isomorphic to the integers, I might as well take G to be the integers, because it's equal to Z up to an isomorphism. Then the subgroups can be described precisely. So all the subgroups. Well, we already discussed that if we take multiples of a particular n, so this is just the set of all multiples of n, say a positive integer, so of the form nz. If we take these multiples of n, that's a cyclic subgroup. It's actually the subgroup generated by n. So these are all the cyclic subgroups, but every subgroup is cyclic, so all subgroups must be of this form. So we know all the subgroups of the integers. They're just multiples of a particular integer. So for example, if I took 5z, which is just all multiples of 5, that's a subgroup of z, and all subgroups look like this. They're all multiples of some positive integer. I could regard this as multiples of minus 5, but I think most people would take 5 as a generator rather than minus 5. Okay? So we know all about the subgroups of Z. Sorry. Without loss of generality. Sorry, I didn't see your hand in the corner. Yeah, without loss of generality. It's a fairly standard abbreviation. But I'm not sure if I've used it before in this class. Okay, so we know all about the subgroups of Z. They're just very simple. They're just multiples of some particular integer, some positive integer if you like. Now the finite cyclic groups are a bit more complicated. So that's what I want to do now. So just to summarize, this was infinite cyclic subgroups. Sorry. Subgroups of infinite cyclic groups, we know all about them. What about subgroups of finite cyclic groups? Well, in the tutorials yesterday, we explored some examples of this, and in particular in the first tutorial yesterday, we looked at some examples in detail of this. I just want to summarize the results. So as I said at the beginning, I'm not going to prove these results in the lecture. The results are proved in Fraley, and I'm happy to go through or talk about the proofs in a tutorial next week, or if you want to come and see me at Espresso Maths, or if you want to email me. Because in principle we should prove everything, and we shouldn't really use a result or be happy with the result until we've seen a proof. But there's also the practical aspects of how long writing out a proof in lecture would take. So I'm happy to go through the proofs in a tutorial or talk about them, but now I'm just going to state a sequence of results which lead to the classification of subgroups of finite cyclic groups. So finite cyclic groups are a bit more complicated than infinite cyclic groups, but it's boils down to just number theory stuff. And the end result is actually very nice. And I will do an example at the end in a little bit of detail to tie all these things together. And then we're going to leave cyclic groups for the moment. Okay, so this is really a summary of the key ingredients. So I'm not pretending to prove anything here, as I've said. So what we're going to have is a finite cyclic group of order n. So that's some positive integer. So we dealt with the infinite cyclic groups. We're now going to take a finite cyclic group of order n. If you wanted, you could just look at integers modulo n. But it's actually possibly easier to use multiplicative notation rather than additive notation. So I'm just going to stick with a general cyclic group of order n. But of course G is isomorphic to Zn, as we've already said. So if you prefer just to work with this concrete model of the group, then that's fine. Anyway, we've got a generator A and it's order n. So remember, that means that n is actually the smallest positive power such that a to the k is the identity element. That came out of the proof last week, that if you've got a finite cyclic group of order n generated by A, then n is the first positive power such that a to the n is the identity. And we've seen that in lots of examples as well. So I'm now going to sequence of results which lead up to the classification of subgroups of finite cyclic groups. So the first result is, which is useful in its own right, is suppose I take an integer s and I look at a to the s. So A is generating my group, so A as order n. What about the order of a to the s? How do we compute the order of a to the s? Well, if you play around with some examples, you'll see what the result might be, and I'm just going to state it. It's actually n divided by the greatest common divisor, or highest common factor if you want to call it that, the greatest common divisor of n and s. Okay? So this is a number theoretic idea on the right hand side, with the greatest common divisor is involved, or the highest common factor. And it's worth playing around with a few examples just to see how that works. And this is very straightforward to prove, but I'm not going to do it now. Well, following on from that, suppose I look at the cyclic group generated by a to the s. So s can be any integer we like here. Well, in fact, all we need to know to compute this group is actually to look at the group generated by the power a to the greatest common divisor of n and s. So the advantage of this is s could be, say, a very large integer, but this is a divisor of n. So this will be between 1 and n. It's a divisor of n. So this reduces the problem of finding the subgroup generated by a power of a just to looking at the case where the power is actually a divisor of n. And the divisors of n are going to play a key role in this classification of subgroups of finite cyclic groups. Okay, so n is some integer like 128 or something. So all we need to look at are divisors of that 128, which is just a case of listing them. Okay, so again, this is not too difficult to prove. You're proving that two sets are equal, so you show that each is a subset of the other. These are both groups, subgroups of the original group, and it's not too difficult to prove that these are actually the same. The next thing that we need as an ingredient is, suppose we've got two integers. It's to say, well, when is it the case that the powers a to the s and a to the t generate the same cyclic subgroup? And again, it comes down to the greatest common divisors being equal. This third one will follow from the first two quite straightforwardly. Okay, so two powers of a generate the same cyclic subgroup if and only if the greatest common divisors of n with the two powers are equal. And this follows from 1 and 2, in fact. One direction is easy, the direction is slightly harder, but not difficult. So as I say, I'm not making any attempt to prove these, I'm just stating them. So these are interesting in their own right, but the reason I'm stating them is so that we can get to the main result. So this is the, sometimes it's called the fundamental theorem. So it's important, of cyclic groups, although really it's a fundamental theorem of subgroups of cyclic groups. So you ought to know this. Well, I'll state it in words and then I'll write down the statement slightly more mathematically. What it turns out is that there's a one-to-one correspondence between, well, we're interested in subgroups of a finite cyclic group, and all you need to look at, as I said a few minutes ago, are the divisors of the other. So you look at the set of divisors, or factors, whatever word you want to use. So remember, n was the order of the group that we were interested in. So we look at the set of divisors of n, which is just a case of listing the divisors or factors of this positive integer. So there's a one-to-one correspondence between the set of all divisors of n and the set of all subgroups of G. So counting subgroups is the same as counting divisors. But there's actually a nice one-to-one correspondence between these two sets. So one of these is a number theoretic set determined by the order n, and the other set is a bag containing all the subgroups of G, and each subgroup will be cyclic. So to be more precise, well, I'm going to write this down in a more precise way. So I'm going to introduce a bijection, a function that will turn out to be a bijection. And there's no standard notation for this, so I'll just call it big phi. So big phi is a function that's going to give you this one-to-one correspondence. So div n this isn't really standard notation either, but this is the set of all divisors of n. And we're going to look at the set of all subgroups of G. So this is the set of all subgroups of G. So this looks a bit complicated, but let me just say what we're doing here. So I haven't finished this sentence yet. So we've got a cyclic group G, so we can look at all its subgroups, and we know each subgroup is cyclic. So this is a bag containing all the subgroups of G. Sub G, so sub for subgroup. G has an order, which is some positive integer n. And just number theoretically, we can look at the divisors of n, all the factors of n. So when I say divisor, I mean positive divisor. And the claim is that these two sets are in one-to-one correspondence with each other. And the one-to-one correspondence is going to be established via this function phi, which I haven't yet defined. So the function phi is going to take